Hello everyone, welcome to Engineering Mechanics classroom. Today we will start with the next unit, that is unit number 4, Analysis of Structures. This unit carries 17 marks. It is divided into 3 parts. First is analysis of plane trusses by using method of joints and by using method of sections. The second part is analysis of plane frames, and lastly analysis of cables. Whereas to start with the analysis of trusses or frames or cables, we firstly need to understand equilibrium of 2-force and 3-force member. So let us see what is equilibrium of 2-force and 3-force member. So equilibrium of 2-force body. Equilibrium of 2-force body. A body is said to be in equilibrium only when the two forces have the same magnitude, the same line of action and opposite sense. In the figure given below, a member AB is in equilibrium due to the action of these two forces F1 and F2. Now for the object to be in equilibrium, the summation of moments should be equal to 0, as well as the summation of forces should also be equal to 0. Now let us prove it. Let us calculate the moment of all these forces, of both these forces, about point A. As F1 is passing through point A, so its moment about A is 0, and obviously the moment of F2 about point A will also be equal to 0. So for this body to be in equilibrium, both the forces should have same magnitude, same line of action, but opposite sense. We can also prove it by calculating the moment about point B, and in the same way we will get the answer that both these forces should have same magnitude, the same line of action and opposite sense. Next is equilibrium of 3-force body. If the rigid body is in equilibrium, is subjected to 3 forces, then the line of action of the 3 forces must be either concurrent or parallel. In the figure given below A, you can observe that 3 forces F1, F2, F3 are acting at points A, B and C. For this object to be in equilibrium, the necessary condition is that these 3 forces must be concurrent or parallel. Now let us prove it. Forces F1 and F2 intersect at point D. So we can find out the moment of all the forces about point D. As F1 and F2 forces both are passing through point D, then their moment about D has to be 0. And obviously if we calculate the moment of F3 force about point D, that also must be 0. So this proves that for this object to be in equilibrium when it is acted upon by 3 forces, then these 3 forces must be either concurrent or parallel. This is a necessary condition for an object to be in equilibrium when it is acted upon by only 3 forces. Analysis of a truss. What is a truss? A framework composed of slender members joined at their ends to form a structure is called as truss. So in the figure given below, we can observe that the vertical horizontal members are connected to each other, and this forms a framework which is called as truss. Now the truss is used for supporting moving or stationary loads. As we can observe in the next figure, this is a truss bridge which is used to support the moving loads. Now moving loads means the load coming from the vehicles which will be passing over this truss. Apart from bridges, the trusses are used to support the roof, the derricks and other such structures. Now when the members of the truss lie in a single plane, that type of truss is called as plane truss. Our syllabus is consists of only plane trusses, so we will analyze plain trusses only. Now let us see the different examples of the trusses. Now depending upon the area where we are going to use the trusses, say for example roof truss, a bridge, or other type of trusses, there are different type of trusses available, namely Pratt truss, Howe truss, Warren truss, and for bridges the same type of trusses having different configuration, that is arrangement of vertical, horizontal and inclined members, are used for supporting the loads coming from the bridges. And lastly, other types of trusses, we can observe the truss in a stadium, a cantilever portion of a truss, or a bascule. Assumptions. For analyzing the truss, we need to make few assumptions which will help us in uh, analyzing the truss quickly and easily. So let us see what are the assumptions. First, all the members of the truss are straight and connected to each other at their ends by frictionless pins. So all the members, they are straight and they are connected to each other at their ends. There won't be any connection in the center of the member. And frictionless pins, or basically a uh, a hinge support that we have already studied in the previous unit, that is the internal hinge, is used for connecting all the members of the truss. These members may be vertical, horizontal or inclined, as we have seen in the picture in the previous slides. Second, all external forces are acting only on the pins. Third, all the members are assumed to be weightless. Fourth, all the members of the truss and external forces acting at pins lie in the same plane. So this is a very important assumption. So from the second assumption, external forces are acting only on the pins. As we can see in the figure given below, any force which is acting on the truss is acting along the is applied on the ends, that is at the points where the members are connected, that means at the pins. All the members are assumed to be weightless. Next, lastly, all the forces, they lie in the same plane. So effectively, as I have told you previously, that in our syllabus we have to analyze only a plane truss. So all the forces are acting in the same plane. Now what are the applicable conditions of equilibrium that can be used for analyzing a truss? As it is said earlier that the forces, they are acting in the same plane, so there are only three conditions applicable. That is, summation of forces along x-axis should be equal to 0, summation of forces along y-axis should be equal to 0, and summation of moment about a point should also be equal to 0. These are the conditions of equilibrium applicable for analyzing the truss. Next, let us see what are the different types of trusses. Perfect truss, imperfect truss. Imperfect truss, it is further classified as deficient truss and redundant truss. Now let us see what is a perfect truss. A pin jointed truss which has just sufficient number of members to resist the load without undergoing any deformation in shape is called as a perfect truss. Triangular frame is the simplest example of a perfect truss. It has three joints and three members. So that type of truss is the example of a perfect truss. But how to identify whether the truss is a perfect or imperfect truss? There is a mathematical formula available for deciding whether the truss is perfect or imperfect, and that is m is equal to 2j minus r, where m stands for the number of members in a truss, j stands for the number of joints, r is the number of support reaction components available for analyzing the truss. So we have only three conditions of equilibrium. So for all the cases of analyzing a truss when all the forces are acting in the same plane, we have three reactions, that is the value of r will be equal to 3. Depending upon the different type of trusses having different configurations, the number of members and number of joints will change. So let us proceed to the next, that is imperfect truss. A truss which doesn't satisfy the relation m is equal to 2j minus r is called as an imperfect truss. So what is imperfectness? When members of a truss are or is not equal to the RHS, that is 2j minus 3. So that type of truss is imperfect truss. Now it may happen that the members are less of the truss, or the number of joints available in that truss are more. So let us see how the imperfect truss is further classified. First one, imperfect deficient truss. As the name says, deficient, it means that something is the number of members are less than the uh, required quantity, or are less than 2j minus r. A truss which satisfies the relation m is less than 2j minus r is called as deficient truss. Such a type of truss will be unstable and may collapse under external forces. Next is imperfect redundant truss. A truss which satisfies the relation m is equal to m is greater than 2j minus r is called as an redundant truss. It can be it cannot be analyzed by using the static equilibrium. That means more than three conditions of equilibrium will be required for analyzing such a truss. Therefore it is called as an indeterminate structure or a redundant truss. Next is an overview of the conditions for stability and determinacy of truss. Now, while analyzing a truss, we firstly need to find out that whether the truss is perfect truss, and or whether it is determinate or indeterminate. So let us see. For a simple truss, m should be equal to 2j minus r. This is the necessary condition. If m is equal to 2j minus r, then it indicates that the truss can be analyzed by using the three conditions of equilibrium, and hence it is called as determinate truss. Next, if m is greater than 2j minus r, it indicates that the truss consists excess members, hence is indeterminate and cannot be analyzed by using the three conditions of equilibrium. M less than 2j minus r indicates that the truss is statically unstable. As we have seen in the previous slide, such a truss is unstable and may collapse. So it does not consist of required number of joints for uh, stability of the truss. If m not equal to 2j minus 3 implies that the truss may consist excess number of joints or members, and hence it is statically indeterminate. Next, here are few examples wherein the determinacy of the truss is calculated. In the first figure, you can see there is a truss. It is supported by two supports, hinge support and a roller support. Roller support is also called as rocker support. So over here 17 members are there, 3 reactions are there, and 10 joints are there. So this satisfies the equation. So this type of truss is statically determinate and stable. In the second example, m is equal to 17. Over here it is same type of truss as the first one, only with an additional member in the central pan, that is the pan third panel. So over here number of members are 17, reactions will be the same, 3 reactions are there, and 10 number of joints are there. So is unstable as it consists of excess members. As we have seen in the previous slide, m is greater than 2j minus 3, that type of truss consists excess members, hence is indeterminate, that is cannot be analyzed by using three conditions of it. In the next third example, there are same 17 members, but the number of supports have been increased. So how many supports are there? 1 hinge support and 3 roller supports are there. So how many reaction components do we have? For hinge support two components of reaction, and for the roller supports, one reaction component in the vertical direction. So three roller supports, so three reactions. So 3 plus 2, 5. In this case, we are getting m plus r, or m plus r is greater than 2j. So what does this mean? M plus r, so 17 members are there, 5 reactions are there, so 17 plus 5 is 23, which is greater than 2 into j, that is 20. So this type of truss consists two extra supports, so it is a redundant truss. It consists of extra supports in this case, whereas in the second case it had extra members. Still it is an unstable structure, and it cannot be analyzed by using three conditions of equilibrium. Let us see few more examples. These are the examples for calculating the determinacy. You can pause the video and you can by your own self see whether the trusses are determinate or indeterminate, and if you have any doubt, you can post me a message so that we can solve your doubt. Next is zero force member. Now, when we will analyze the truss, we will come across an arrangement of members wherein the forces in the members, that is the internal force in the member, might be zero. So there are few special cases, or I should say there are conditions wherein we can identify such zero force members. Now, when once we will analyze the truss, we are required to analyze, or we are required to find out internal forces in the members as well as the external support reactions. So once we know that a particular uh, number of members of a truss are zero force members, then it will reduce our time required for analyzing the truss. So let us see what are zero force members. In the first case, you can see there are, in the first figure you can see there are three forces acting at a joint J, and there is no external load which is acting over here. So if you apply summation fx over here, you will get Faj is equal to Fbj, that is the two horizontal forces which are acting away from joint J. The first one in the left direction is Faj, in the right hand side Fbj. So if you apply summation fx, you will get Faj is equal to Fbj, and the third force, that is Fcj, that force will be equal to 0. If you apply summation Fy, you will get the value of Fcj as equal to 0, as there is no external load acting on the joint. If there was an external load acting on the joint J in the downward direction, then the value of Fcj would will so Fcj will have certain value. But in this case, there is no external force acting at joint J, that is why Fcj will be equal to 0. Second case, you can see again at there's a joint J, and in the second example there are four forces which are acting in different directions, but you can observe that the line of action of these two forces, say for example Faj and Fbj, is same, but they are acting in opposite direction. Similarly, Fcj and Fdj, they are passing through the same line of action, but they are acting in the opposite direction. So for such a joint, the value of Aj will be equal to value of Fbj, and for Fcj will have the same value as Fdj. So this is also one important case that we may come across while solving or analyzing the truss. So we need to keep this thing in mind. Now the last case in which you can observe there are only two forces at this joint, and one is horizontal and the second force is inclined. The horizontal force is Faj, the inclined force is Fbj. As you can see, there is no external load acting on this joint, so both the member forces will be equal to 0. If you apply summation Fx or summation Fy, we will get the value of Faj and Fbj equal to 0. So these are the three cases, important cases that we need to remember while analyzing a truss. Now, moving on to the next slide, that is methods for analyzing a truss. So there are two methods for analyzing a truss. First one, analysis of a truss by using method of joints. Second, analysis of truss by using method of sections. So let us see the first one, that is method of joints. Now over here, as the truss is in equilibrium, so if we isolate the different parts of the truss, that is if we isolate the members, horizontal, vertical or inclined member, or the joints of a truss, so these joints should also be in equilibrium. That is the necessary requirement for the truss to be in equilibrium. So this method of joints works on this principle that if the truss is in equilibrium, then its joints should also be in equilibrium. So for this method, let us see what are the different steps. There are 8 steps. The first one is to check the stability of the truss. As we have seen, n is equal to 2j minus 3, where n is nothing but the number of the members in a truss. We can also write m in place of n. In case of a cantilever truss, we can check the stability by using n is equal to 2j minus 4. The second step, we need to draw the FBD of the entire truss, mark the reaction components, and then we need to apply conditions of equilibrium to find out the magnitude of the support reactions. Then step number 3, we need to select a joint in such a way that not more than two forces are acting on the joint. Okay, so this is the step number 3. We need to isolate all the joints one by one, and we need to start with a joint in such a way that that joint carries not more than two unknown member forces. So we can apply summation fx and summation fy to find out the unknown member forces. Remember, while analyzing the truss, we need to find out the support reactions as well as the member forces. If there are 10 members, so we need to find out the magnitudes of the forces in all of these 10 members. Let us see what is the next step. Step number 4, we need to draw the FBD of selected joint by assuming forces in members as acting away from the joint. That is, we are assuming these members are carrying tensile force. We need to draw the free body diagram of all the joints in such a way that we represent or we draw the member forces acting away from the joint. Next step, the forces at a joint are concurrent and each joint is in equilibrium, so we can apply conditions of equilibrium, that is summation fx equal to 0 and summation fy equal to 0. As we have discussed it earlier on, that only 3 conditions are applicable to the truss, but once we are analyzing a joint, we have only 2 conditions, that is summation fx and summation fy. Next, what we need to do, next step, find out some forces by observation or by inspection. As we have seen in the previous slide, 0 force members. If there is a similar case, depending upon the arrangement of the members, we need to identify 0 force members, or we need to identify the member forces by observation or by inspection. Next step, repeat the procedure by selecting different joints and find out the forces in all the members of the truss. Lastly, we need to tabulate the results in a force table using positive as tension and negative as compression, and we need to mention the nature of the forces of a truss. So these are the 8 steps that we need to follow while analyzing the truss by using method of joints. By method of joints, in exam it may be asked for 6 or 7 marks depending upon the number of members in a truss. So let us see one example on method of joints. So this is the example. Use method of joints and determine the forces in each member of the truss. Now over here I have directly shown the solution. You can see there is a truss which has members A, C, D, B, E, and external loads are applied at point C, D, and E. At point A, we have a hinge support. That is why two components of reactions are shown, AX, AY. And at point B, we have a roller support. That is why we have shown one single reaction acting in upward direction. Now, this figure is the free body diagram. That is a part of solution. I have directly drawn the free body diagram. Now, over here you can see we have isolated the truss from its surrounding and we have shown the reaction components instead of the supports. So the first step is to check the stability. So let us count the number of members. How many members are there? AC, AE, CE, CD, DE, EB and DB. So total 7 members are there. Number of joints: joint A, joint C, joint D, joint B, and joint E. So 1, 2, 3, 4, 5 joints are there. Now let us substitute the values of M and J in our equation. That is, M is equal to 2J minus 3. So we get that the truss is a perfect truss and it can be analyzed by using the 3 conditions of equilibrium. So our next step is to find out the support reactions AX, AY by applying conditions of equilibrium to the entire truss. Now this is an important step. We are applying conditions of equilibrium to the entire truss. Okay, and by applying summation of moment at point A, we got the value of RB as 40.5 kilonewton, and it's acting in the upward direction. So our assumption is correct that RB is acting in the upward direction. Now by applying summation Fy, we got the value of AY, that is 3 kilonewton, which is also acting in the upward direction. Since there is no external horizontal force acting on this truss, that is why value of Ax will be equal to 0 as we apply summation Fx equation. Now from this third step, our method of joints will start. The first 2 steps are general steps that we need to follow in almost all the type of analysis of a truss examples. Over here we can isolate joint A or we can isolate joint B. What is the condition for isolating the joint? The joint should not have more than 2 unknown member forces. As you can see in the figure below, at joint A we have AX, AY, the values of which we have already calculated. Apart from that, we have 2 unknown member forces, FAC, FAE. Now, as per our assumption, we have shown the direction of FAC acting away from the joint. As we are analyzing joint A, so from A, we have shown FAC to act in the direction away from the joint. Similarly for FAE. Now, we will apply both the conditions of equilibrium, summation Fx and summation Fy, for finding out the unknown member forces FAC and AE. By applying Fy, we got the value of AC as minus 41.57 kilonewton. And by applying Fx, we got the value of FAE as 20.785 kilonewton. Now, what does this mean? FAC we got the value as minus 41.57 kilonewton. That means we have assumed FAC to act in a direction away from the joint. That is, it carries a tensile force. But after analyzing, we got the value as negative. This negative value implies that our assumption, that is FAC acting away from the joint, is incorrect. Okay, please don't get confused with the negative sign. It is just a representation that our assumption is incorrect. We need to our assumption is incorrect. FAC is acting towards joint A. That means it is carrying a compressive force. Whereas FAE, we got a value positive 20.785 kilonewton. That means our assumption is correct. It is acting away from the joint. Now focus on the equation of summation fx. See what we have written. FAE plus FAC cos 60. Now, though we got the value of FAC negative in the first step itself, despite of that, we should not change the direction of the forces in the FBD. And in the same way, we need to use the same components that we have shown in the FBD. Now from the FBD you can see FAC is acting away from the joint, so its x component and y component will be positive, that is FAC cos 60 and FAC sin 60. So while calculating the equation ahead, we should not change the direction of FAC. We need to substitute its value, whatever value we got positive, so we will substitute the positive value. If we get negative value, then we will substitute the negative value. So in this way we need to proceed. Let us isolate the other joint. Now we have an option to isolate joint C or joint B. Second, we'll consider the joint C. Now you will see that at joint C there are three member forces FCA. Now see the naming is changing. When once we were solving the support A, we called the member force as FAC. Now when once we are solving the joint C, we are calling the same force in the member as CA, whereas it carries the same magnitude as we have calculated in the previous step, but with a negative sign. As this is our assumption that we need to assume the direction of the force is acting always away from the joint. If we get a positive value, then it represents that our assumption is correct and the member is carrying a tensile force. If we get a negative value, which indicates that our assumption is incorrect, the member carries a compressive force. So in this way we isolated joint C, we applied summation Fy equation and summation Fx equation to get the unknown member forces. Similarly, we isolated joint D to get the unknown member forces FDE, FBD. Next, now we are left with only one member force, that is EB. So for that we again need to isolate the joint B and apply conditions of equilibrium to get the value of the force BE. Now over here you can see we have firstly applied summation Fx, we have substituted the value of FBD that we have got as negative, and then we have calculated the value of FBE, that is 23.383 kilonewton. Now there is a check that has been performed just to understand that the answer that we are getting is correct or incorrect. So over here you can see summation Fy is equal to minus 46.766 sin 60 plus 40.5. So we got the value of summation Fy equal to 0. That means whatever value we have calculated of FBE is correct or FBD is also correct. It is not always required to perform such a check. If you have any doubt while analyzing the truss or the joint, you can carry out such a check, but it is not expected in the solution. So moving on to the last step, that is the force table. Now we need to tabulate the values of all the member forces that we have calculated with their nature. So we got the value of AC as negative. So 41.57 is the value, which implies that it is a member which is carrying compressive force. So we have indicated the nature of the force by writing capital C, which stands for compression. And if we write capital T for any of the member forces, it indicates that the member is carrying a tensile force. Okay, so this is one example on method of joints, how to use method of joints. So let us quickly revise the all the steps. Firstly, we need to draw the FBD of the entire truss, represent the forces acting on the truss as well as the components of the reactions, that is the support reactions. Check the stability of the truss. Next, we need to find out the values of the support reaction. Then, in the next step, that is step number 3, we need to isolate a joint depending upon the condition that it should not have more than two unknowns. Now, it depends on you that you can start from the left end or from the right end. That is, in this case, you can isolate joint A first or you can isolate joint B first. Both the ways are correct. But after that, we need to make sure that whichever joint we are isolating, it should not have more than two unknown member forces. And we have to proceed in the same way, go on isolating the different joints present in the truss by which satisfy the condition, and then apply summation fx and fy on those joints only to find out the unknown member forces. Now we have assumed the direction of the unknown member forces to act away from the joint. That means we are assuming that these members, they are carrying tensile force. Now over here I've provided you with the three examples practice problems, and I've provided you with the answers of uh, the member forces that are required to be calculated. Now all these three problems you are required to calculate the member forces, and you can check the values given over here. Now let us move to the next slide, that is analysis of truss by using method of sections. Now in this method, this is a method which is quite I should say, yes, easier, and time it reduces the time required for analyzing the truss. Now this method is mostly used when we are required to find out the member forces of few members. Let us say a truss may contain 10 members, so we are interested in finding out the magnitudes of only 3 member forces. So in that case, if we proceed by method of joints, then it would be very laborious, it would be more time consuming. So instead we will go for using method of sections. So the first two steps for method of sections are the same: check the stability of the truss, draw the free body diagram, and apply conditions of equilibrium to find out the support reactions. Now in the free body diagram only, we need to mark the member forces that are required to be calculated, and then draw a section line which will pass through these members. What is the condition for this section line to pass over the members? The section line should not cut more than 3 unknown member forces, which are to be determined. Now it may happen that a section line is cutting 3 members, but only 2 are required to be found as per the question. Okay, so it doesn't matter, we can cut the truss along that section. Now what are we trying to do? We basically are trying to cut this truss in two parts depending upon the number of unknown members required, and then we are going to apply all the three conditions of equilibrium on any one part of the truss. Now let us say we are cutting the truss from the center, so it will divide the truss into two parts. So in the next step we will draw its FBD of any of the section, that is the left hand side section or the right hand side section, and we will apply all the three conditions of equilibrium. Okay, so select a section, cutting maximum three members such that uh, all the three are unknown members, and it should not cut more than three members. Okay, so this is the condition. With reference to the imaginary section, now there are two parts of the truss. As I told you, select either of the parts and draw FBD of that part by assuming forces in the cut members as uh, towards the section line, that is acting away from the joint, as we had assumed in the uh, previous slides. For analyzing the truss by method of joints, we had assumed all the forces to act away from the joint. So in this method of sections also we need to assume that the forces are acting away from the joint. That means the members are carrying tensile force. So see to it that the free body diagram that we have drawn of any part of the section of the cut truss, it should represent the support reactions, the external loads which are acting only on that part, and the unknown member forces. Then lastly, we need to apply all the three conditions of equilibrium to find out the member forces. Now apply summation of moment equal to 0 at different joints to find out the internal forces. Okay, and there is an important tip. A section can be cut more than three members, but the unknown forces should not exceed three. Now as I told you that it may happen that more than two forces are acting on the joint, uh, that is more than two members are connected at a joint, so it may happen that more than three members are getting cut by the section line, but the unknowns should not exceed more than three. So this is care that we need to uh, take care while drawing the section of the truss. Now let us see how to use this method by using one example. Okay, so this is a truss. Over here it is said that we need to determine the forces in members FH. FH, you can see it's an inclined member at the bottom. DH is the vertical member. EG is the horizontal member, and BE is again the inclined member. Now in this example you can see SI system of units is not used. You can see the measurements and the magnitudes of the forces, they are given in kips, and the distances between the joints as well as the supports is mentioned in feet. So either you can keep the same system of units and analyze the problem, or you can convert the units, that is feet to meters and kips to newtons or kilonewtons, as the case may be. But over here I have kept the same system of units. So firstly we need to draw the free body diagram, and as you can see I have tick marked the members, that is DH, FH, EG and BE, which are to be found by using method of sections. Next we need to find out the support reactions by applying all the three conditions of equilibrium. Now, one thing, we have drawn a section line over here, represented by a red colored section. You can call this section as section 11, section XX, or you can name it accordingly. But note that the members DH and FH, one is inclined, the other is vertical. So what we can do is that we can pass a cutting section that we'll see ahead. The nature of this section line can be a straight line, or it can have a curve, as may be required depending upon the arrangement of the members. Okay, so that we'll see ahead. uh, Now we have calculated the support reactions. Now we need to cut the truss, and we need to apply all the three conditions of equilibrium. So over here you can see that we have drawn a cutting section between the members BD and CE. Okay, and now we are going to consider the top portion of the section. As you can see in the right hand side, we have shown the top portion of the section line. So over here you can see we have drawn the truss as it is, and we have shown only those member forces which the section line is cutting, that is TBD, TBE and TCE. In addition to that, we have shown the external forces which are acting on the joint, as it is a free body diagram. So whatever be the external forces acting on the joints, we are required to show them in the free body diagram. Next, now to analyze or to find out the member force TBE, what we can do is that you can apply summation Fx, Fy and moment equation. But it is mostly advisable that you firstly apply the moment equation, so that we can quickly get rid of one of the unknowns or two of the unknowns. Now over here we have an option of calculating the moment about the joints A, B and C. Now if you calculate the moment about joint A, the member force TCE will be 0. So we are left with only two unknown members, that is TBD and TBE. The second thing is that you can also calculate the moment about the joint C. Okay. For that case also, the member force or the moment of the member force TCE will be 0. Then again we are left with the two unknown members TBD and TBE. So you can select either of the joint A or joint C for calculating the moment. But over here I have selected joint A, and by using the moment equation you can get the value of CE. Now why we have selected joint A? Because TBD, that is the line of action of TBD, is passing through A, so its moment will be equal to 0. Also TCE is it's passing through the joint A. Again the moment of TCE will also be 0. So we are left with only one unknown member force which is required to be calculated. So simply by rearranging the equation, we can get the value of the member force TCE, and we got the value as negative, which implies that our assumption is incorrect. This member TBE is carrying a compressive force. But again I'm telling you, again I'm repeating that we shouldn't change the direction of the forces that we have shown in the free body diagram. We need to keep them as it is. We need to carry the negative sign with these member forces ahead if required in the equation. For finding out the unknown member force HF, we are drawing a cutting section between the members HD and IG, and considering the bottom portion below the section line, we have drawn the free body diagram, and we can observe that TIF, TIG are passing through point I, and we are required to calculate the unknown member force THF. So instead, using the two equations summation Fx and summation Fy, we will directly use summation of moment about point I so that the two forces TIF and TIJ, as they are having the line of action passing through point I, their movement would be 0 about point I. Hence, we'll be left with only one unknown, THF. So, by finding out the movement about point I, we get the value of THF, that is 2.5. And in this way, we have found all the unknown member forces. So, depending upon the number of unknowns, it may be required for us to use more than one section line. And in some problems, one section line would be sufficient for finding out the unknown member forces. So, this condition varies from problem to problem. Next, I'll provide you with some practice problems. You can pause the video and note down the problems for your practice. That's it for trusses. Thank you. If you have any doubt or queries, you can contact me.